When I was a kid, I really liked to draw. I had a big box of pencils, ink pens, marker pens. When I think back of it, it is fascinating that without thinking, I took any pen out of the box and put it on the paper and just started drawing. Even with the many different kind of pens, no one needed to explain to me how to do that. Now, pencils leave a trail of graphite on the paper, pens use ballpoints, and felt tips distribute ink through some fiber. Now, even with the different materials and distribution mechanisms, all drawing tools just need to be put down on the paper and moved around. That is an interface between the user, which is the hand, and the technical stuff inside the pens. Now, some call that abstraction. But when a kid learns this for the first time, this is not very powerful yet. All that is gained is that the technical details are stored invisibly inside the pen. That is called encapsulation. And that's a good thing, so we keep the ink in the pen and not on the carpet. So where is the abstraction then? Well, it is in the fact that all these different kinds of pens have the same shape. You can grab a pencil or pen or a marker and you put the tip on the paper and by miracle, shapes appear. So you hold and move the pen, but it is the pen that has the technical implementation how to distribute ink or graphite. Now the best thing is that the box with all the pens can have any type of drawing tools. Pens can be added or exchanged. It does not matter. All that matters is that they implement an interface, which is that they can be held and have a tip to put on the paper. As far as the user is concerned, there is only the interface, which is the outside of the pen. Now, if there is a user, the hand, and there is an interface, the outside of the pen, and a technical implementation in the pen, then the question is, who designs the interface? When an interface is used to hide the technical stuff in the pen, it is natural to first design the technical stuff and put an interface around it. But as I have said before, this is just encapsulation, hiding technical stuff. A good interface is made before the technical implementation. The pen is a good example of this. Pens did not grow on trees and the human hand evolved around it. It was the other way around. There is a human hand, the user, that needs a writing tool. The interface is specified by the user. The pen implements that interface. When interfaces follow from what the user needs, the abstraction is discovered. Perhaps after many tries, this is the way to interact with all writing tools. With software, it is no different. Abstractions are great, but be cautious to design them everywhere. Inserting interfaces everywhere allows very modular design, but it also adds a lot of extra code that you have to chase around. There is something called the rule of three. When you start to notice that two objects start to behave very similar, just accept the duplicate code and how to interact with it. You can add switches in the code. Do this for one and that for the other, and don't worry about it yet. When a third object starts to behave as the previous two, make the abstraction. The benefit of waiting is that the commonalities present themselves. They are discovered because they are obvious now, and it is more likely that the abstraction can now be made with the user in mind. What does the user need to work with these individual pens? This in contrast with creating an interface to shield the technical stuff in the pen. Now, of course, there are exceptions to the rule. If you know from the start that you're going to build a pluggable system where many different objects have to behave in a similar way, you have to design the abstraction first. Now, in a language like Python, abstractions can be found everywhere. For example, take containers like tuples and lists. The user, which is the developer, has some needs, like creating a list, get elements at an index, sizing. These functions are the container interface. It is the job of the tuple and the list to implement that interface. The tuple and the list are concrete data types, and the container interface is the abstract data type. The same goes for numbers. You can calculate with ints and floats. Both are very different things, and still you can all treat them as numbers. An int is a concrete data type with very specific operations, and a float is also a concrete data type with its own unique implementation. What they share is an abstract data type called number, which leads me to another kind of abstraction in Python. One of the things both number types have in common is dunder string. Have you ever thought about why you can just print any object in Python and it just works? When you print an object, at some point dunder string is called in that object. The class that was used to create ints and floats can implement the required code to retrieve the number and format it in a readable way for the user. The abstraction here is that the user just wants to print an object. The print function then dispatches this call to dunder string in the object. Now this is called polymorphism. The method is always called dunder string, but each object may implement how it sees fit. So now you know three things. Abstraction decouples the user from internal workings. Abstraction can be designed upfront or discovered later. And abstraction is found everywhere in Python. Now, one of my students once said, "Oh, this is all so abstract." Now, before he could even realize his own joke, I thought, you got that right. See you next time.